Yes, love it. If you are new, you may not know that we have lithographs, pretty pictures from Hubble available on table over there and the table down here. Tonight's lithograph is the Interacting Galaxy NGC 7714. If you want to know about, one of your favorites, right? If you want to know more about the galaxy, there's a few hundred words of text to describe it and another image on the back. If you didn't get one on the way in, grab one on the way out. Also, over there we have some Eclipse information that will tell you remind you some of the stuff that we're going to tell you in the talk tonight. These printouts are over there. You can grab them on your way out. Because tonight's talk is the 2017 total solar eclipse, Chasing Shadows Across America, by myself, Carolyn Slavinsky, and Jessica Kenny. We have a round-robin tag team presentation for you tonight because there is just so much to cover about the solar eclipse. Next month, we have a very special speaker coming in from Yale University, Priyamvada Natarajan, on mapping the heavens. And this is very special. We usually don't have any budget to bring in people from out of town. So when they're willing to come in from out of town and give a talk, this is fantastic. In March, Lauren Corleys is coming not from out of town, but from across the street at Johns Hopkins University, and she has yet to give me the title of her topic. She said she was going between a couple, and she hasn't given me the final title. And in April, we have David Law from the Space Telescope Science Institute talking about integrated field unit spectroscopy. I know that sounds a little intimidating, but as we take advantage of computers and new electronics, we can do amazing things in astronomy, and IFUs are part of the future, okay? So you want to know the future of astronomy? This is a big part of it. To find out all this stuff, you can go to our website. If you just search Hubble Public Talks or Space Telescope Public Talks, you'll find this webpage where we have the list of the upcoming lectures, the link to the live webcasting, the archive of our webcasting, which goes all the way back to 2005. All right, that's 11 years worth of astronomical goodness for you to explore. And you can also subscribe to our public lecture series announcements to be reminded of things like, oh, hey, we're not having it on the first Tuesday in January. We're skipping to the second Tuesday because nobody was around last week, both because of the holidays and because the American Astronomical Society meeting. So the first week in January is often one that I will postpone 1 week. Okay, email announcements. I already gave you the easiest way to sign up. You can also go to this place, maillist.stsci.edu, to do so. If you would like to send us email, you can send it to publiclecture@stsci.edu, and it will get forwarded along to me and one or two others who answer questions to that email address. All right. Social media, we have on Facebook and Twitter and Google Plus and Pinterest. Do we have others? We may have other social media feeds. I've got my blog on Hubble site. I'm also a little bit on Facebook, Google Plus, and Twitter when I have the time. Certainly did not have any time today, so but I'll get to posting a little bit on social media tomorrow. The weather is not permitting tonight. If you looked up as you came in, you saw no stars. It's clouded out, so we will not be going across to the Maryland Space Grant Observatory after the talk. The Maryland Space Grant Observatory does have a website, md.spacegrant.org, and they do public observing most every Friday. Please go to their website and find their public observing. If you can't, since we can't do it tonight, you may be able to do it on another day this month. All right, News from the Universe will return next month. I know I wasn't here last month to give you News from the Universe, so it's been since November, but we spent so much time prepping this talk today and yesterday and the day before and Friday that I just wasn't able to make the time to do News from the Universe, so I apologize. I'll give you a really great one next month, okay? All right. In the meantime, I will introduce our featured speakers, and I will switch slides. All right, our speakers tonight are myself, an astronomer in the Office of Public Outreach. Carolyn Slavinsky, stand up and say hi. She's an education specialist in the Office of Public Outreach. And Jessica Kenny, another education specialist in the Office of Public Outreach. Is that your title? Education Outreach Specialist. Okay. So we are three of the, 20, 25 people in the Office of Public Outreach. And we recognized when we had this gap in the schedule, we didn't have a talk for January, that we needed to, well, wait a minute, we got this amazing event coming up in August of next year. And we needed to fill that in. So we actually utilized about 6 more people's knowledge in pulling together lots of information about this. Somebody was commenting beforehand, well, this is 8 months away. Do we really need to talk about it now? Yes, you do, because if you're going to go see this total solar eclipse, you want to plan in advance. Matter of fact, just last week at the American Astronomical Society meeting in Texas, where Jessica was there, they had a huge session that was packed, sold out, standing room only session of people sharing information about what they're going to do for this total solar eclipse. So it's not too early to plan. I've already got my reservations for where I'm going to be for this eclipse, and hopefully we'll give you enough information tonight so you can decide where you want to be for this eclipse. All right, so let's start with the basics. There will be a total solar eclipse on August 21st, 2017. It will pass across the entire continental United States. It will start in Oregon and go through South Carolina. It will have its greatest duration in Illinois, Kentucky area, 2 minutes and 40 seconds of total eclipse. All right? This path of totality that is being drawn here is only 71 miles wide. All right? However, the rest of North America, all the rest of things that aren't on this line, will get a partial solar eclipse. Okay? This is the first coast-to-coast solar eclipse since 1918. So I'm told. First coast-to-coast total solar eclipse since 1918. All right? There haven't been really good solar eclipses lately in the United States. This is something special. All right? And so what's going to happen? All right, well, this is the first part of it, is going to be a partial solar eclipse. This is the limb of the moon passing in front of the sun. And partial solar eclipses are much more geographically common because they can be seen across a much, much, much larger region. What makes this eclipse special is that this eclipse will go through into not only cover part of the sun, but cover the entire sun. The moon will cover the entire sun, exposing the outer parts of the sun, the atmosphere of the sun, called the solar corona. And the solar corona is just amazing to behold. If you have really good photographic skills, you can see all sorts of amazing striations. This is material flowing away from the sun in the solar corona. And there's amazing photographs of the sun during a total solar eclipse. This isn't just a black spot put there. That's actually the moon, all right? And you are seeing the material flowing away from the sun in the solar corona. You also could see some other really cool effects. One of the most famous is the diamond ring effect. Just before totality, or just as totality ends, you can get a bright spot with this ring around here, all right? And you get a beautiful diamond ring effect. You can also get, at the same time, something called Bailey's beads. All right? And this is due to the uneven topography on the surface of the moon. There are mountains on the moon. The moon is not this perfect sphere as it was imagined back in ancient Greek days. It actually has topography, and you can see the light shining through the hills and valleys on the moon just as it goes into and out of totality. Here is a nice little time sequence showing from left to right as the moon passes over the various topography of the moon, creating these Bailey's beads. Sometimes also you can actually see the very inner atmosphere of the sun and this are the solar prominences, because the corona extends well out from the sun, but right above the sun you can get these fingers of hot plasma up from the sun, and these red regions right here, that is that hot plasma seen in H-alpha radiation here, I believe, that's extending above the sun. You can actually see the fingers of plasma extending above the sun when the moon blocks it. This is also, this happens particularly when you have an eclipse that's just slightly an annular eclipse, and I'll tell you what an annular eclipse is on the next slide. All right, an annular eclipse is sometimes when the moon is a little bit further away and can't cover the entire sun totally. All right, it doesn't become a total solar eclipse, so you get this thin ring around it, okay? And so when the moon is just at the right distance, that it just gives a tiny little bit of annular around it, that's one of the times that you can see these prominences extremely well, because you just get a little bit of the photosphere and the material extending above it for these solar prominences. So a total solar eclipse is an amazing event. It is a very rare astronomical occurrence, and folks who've been to them can get really religious about them, okay? I had a professor at Berkeley who, would travel all around the world to see his next total solar eclipse, okay? We're gonna talk about a gentleman named Fred Espenak, who is called Mr. Eclipse. He's been seeing eclipses since the 1970s. They go all around the world, they chase around the world, it's an enthralling experience, okay? And they're just totally into seeing these eclipses. All right, so what is the basis of this? It's just a cosmic coincidence, okay? There is no reason we should be able to see these total solar eclipses, except we have this wonderful coincidence, all right? Now, contrary to what Hollywood tells you, the moon is not that big on the sky, okay? This is totally faked, unfortunately. The moon is actually relatively small on the sky. And if you overexpose the moon, okay, this is an overexposed moon at nighttime, it could end up looking a lot like the sun at sunset, okay? So there's the moon, and there's the sun. There's the moon, and there's the sun. And what do you notice? They're about the same size on the sky. The moon and the sun are about 30 arc seconds across, half a degree, 30 arc minutes across, half a degree, okay? All right, they are about the same size on the sky. And this is totally happenstance. That's totally circumstance, and it's true now. It actually won't be true, 100,000 years in the future, because the moon is actually moving away from Earth, okay? There will be a time when the moon is not big enough to create a total solar eclipse again. It'll be thousands of years in the future. During our lifetimes, it'll continue to be true, all right? Oh, and by the way, this is the color of the sun. Right? You'll see a lot of depictions of the sun as being yellow. All right? That's not what the true color of the sun is. All right? It's what we think of the color of the sun being. But this, if the human eye could see the sun, this is a rough approximation of what the sun's color would be. So I've tried to use this, although I will apologize. There are a lot of graphics that we got from other places that have the sun colored bright yellow. But you guys know it's not bright yellow, okay? You know that this is the light whitish peachy color that the sun truly is. All right, so what are the geometry of it? Well, it's really quite simple. Moon orbits around Earth. Earth orbits around the sun. And when the shadow of the moon falls on Earth, we get a solar eclipse. Straightforward, easy, right? You just don't appreciate it, just how hard this is, okay? For one major reason. These diagrams are totally not to scale, all right? To understand just how amazing this coincidence is and how refined the geometry has to be, we got to tell you about the size scale of the universe. And for that, I'm going to bring up my compatriot, Carolyn Slavinsky.
Can you give me the clicker? assume that's forward, backwards.
Yep.
Easy way. All right. So the last 3 slides that Frank showed you had that same phrase on the bottom, not to scale. You're used to seeing images like this because it would be really, really difficult if there were an image that actually showed the true scale. So let's take a little bit of an exploration here to see what that means. All right. A typical map of the United States. Is there anybody in here who is from Alaska? No. Knows anybody in Alaska?
There are probably people on the webcast from Alaska.
Could be. Want to visit Alaska? Excellent. So those of you who may be online and are from Alaska, you're probably annoyed every time you see a map like this, because if you really wanted to show what Alaska looks like relative to the US, it's not the size of Ohio or so, it's that big. So this is a typical representation, or this one is a typical representation, but this is a much more realistic representation. But it would be hard to get a piece of paper that would fit it all, and the rest of the US would get very, very small. So we're going to now utilize the props that were over here, which are all sadly in the shade. So can we move it without dropping all the balls? Here's the magic part. We're going to go a little bit my way.
Okay, your way.
How's that? Can everybody see the balls now? All right. This is my daughter's old basketball. So if the sun were shrunk down to the size of a basketball, now this is something that I can hold, we can see inside the room as a reasonable scale. I want you to start guessing. If you see any objects up here that might represent how big the Earth would be compared to a sun that's this size. So anybody want to take a guess? A few of these are my dog's toys and other, there's a bead on top of this eraser, the little green thing. It's the smallest thing I could get that I wouldn't have to worry about it rolling all over. Anybody want to take a guess? What do you think?
Second to last.
Second to last. This guy? Incorrect. Frank will now juggle for you. All right, anybody else want to take a guess? One of these 2 balls? Yes? No? Smaller one? Okay, we're getting votes for everything. How about the one that looks like a jawbreaker, but it's not? Reasonable? Maybe yes, maybe no? All right. Well, turns out Frank is holding Jupiter. Now, we all know Jupiter is a really big planet. So that's the comparison of the size of the sun to the size of Jupiter. Well done. This is still too big.
This is Jupiter.
If this is the sun, that would be Jupiter. This would be closer to the size of Earth, but still not there. So the actual size of the Earth and the moon would be so small that we wouldn't be able to manipulate them, and you would never be able to see them without coming right up and looking under a microscope or something. So we're going to use a completely different scale. This is as big as I could get on the screen. This is now about 9 feet across. We were now to blow the moon up, or the sun, from the size of a basketball now to a 9-foot wide ball. Now do you see anything on the table that looks like it might represent the size of the Earth? Anybody want to take a guess? You took a guess before, so I'm going to go ahead and pick on you. What do you think?
The same.
The same one. This guy? Excellent choice. This is roughly the size of the Earth. Go ahead, Frank. You may.
Just trying to help.
Thank you, thank you. Look how tiny it is. It's very small. So you remember the map of the US and Alaska and how hard it was to get them all in one place. So imagine a piece of paper in a textbook or something that's showing the true sun size to scale and the Earth to scale. What's that? Ready?
And this would be?
Take a guess.
Jupiter.
Very good. Pose for your pictures. I like that. Very good. Very good. All right. So we just answered those 2 questions. If the sun were 9 feet across, about how big would the Earth be? Now we're looking at the Earth. So Anybody have a guess on the moon? It's really only one choice left. It's the little bead that's on top of this eraser. So this was about 1 inch across. This is about 1/4 of an inch across. And that, again, is a 9-foot globe. So clearly difficult to get all in one page. All right, so this is another representation giving you actual sizes, true photo of the sun with a little dot thrown on it that would represent the relative size of the Earth. And that's the Earth blown up to 10 times bigger. And this is another representation of the size of the Earth and the moon. All right. So here we have one picture that throws them all together. And again, if you were to try to fit this in a textbook, you'd have a really hard time. And in fact, can anybody even see where Earth is? If you're walking right up, Mercury, Venus, Earth. That little tiny thing right there really excuse me? Okay. So you can see the need for scale. This is another actual photograph. This was taken by Galileo back in 1990. Galileo, the spacecraft. I realized as soon as I said that, like, you know, I didn't even try to make a joke. It just kind of hit me. But this was taken in 1990. Frank provided this image to the presentation, and what he said was that the image of the moon had to be, the brightness needed to be bumped up quite a bit because the relative brightness was so faint you wouldn't be able to see them both. But this is a single image, not a composite, not an illustration, an actual photograph taken by the Galileo spacecraft back in 1990. All right. This is another factoid that we're going to use to our advantage, and Jess is going to help me out with this part too. So we have the size of the Earth and the size of the moon. The Earth is our 1 inch relative model, and the moon is our 1/4 inch relative model. And if you were to line up the Earth 30 times across, that would be how far you'd have to go before you get to the moon. So instead of our fancy balls, we now have a yardstick model. So we're going to do the most elementary kind of math, but we're going to need a volunteer to come up and help us do this part.
We have a bunch of kids. Come on. He wants to volunteer.
I got the first volunteer. Come on up. And
You want me to switch to?
well, we don't need the bright screen yet.
Just, yeah, I was thinking.
Just yet.
Wait till he.
Tell me what your name is first.
Alex.
Alex. Okay, turn around. Everybody say hello, Alex. All right, Alex is going to be our volunteer here. Jess, why don't you stand over where the light is on that side, yeah, so we're not completely off the side. All right, so Jess has a model of a yardstick that has a 1 inch ball on one side of it, and she has another stick with a 1/4 inch ball on it. So guess what these are representing? The Earth and the moon. Now, we said that the Earth and the moon are about 30 Earth distances apart from each other. So if we have a 1 inch Earth, how far away would the moon be? 30 inches, very good. So the Earth is now set at the 3 inch mark on the yardstick. So where does the moon go? You guys are so good. All right, so there's a clip. All right, we now have an actual scale model of the Earth and the moon and how far apart they are from each other. All right, so now, Alex, now comes the part where you really have to do some work for us. We need a solar.
We need a sun, don't we?
Yeah, we do.
All right.
But
You want me to
the map's the next thing yet, right?
Map is the next thing.
Yeah,
we
so I
need
don't want
slides.
that yet. Okay.
Okay. So you want to talk about the map first?
No, not yet.
Okay.
So the next thing we need to do to really figure out what the scale of this is, and I don't have anything that you will be able to point to. Anybody have an idea how far away the sun would be for an Earth-Moon system of this size? Would it? But first of all, okay, who thinks it would be inside this room? Who thinks it would be inside this building? Who thinks it would be somewhere across campus? Who thinks it would be in another city? Who's not going to vote? Thank you. All right. Always play safe. Okay. Anybody want to take an actual guess of how far? Give me like a distance.
We had a lecture here some years ago where the speaker used a grapefruit, and he stood over there where the basketball was,
Okay.
and then he had somebody walk all the way around the room and wound up over here with something the size of a pea or something like that.
Yeah, so that would have been
Okay,
the
but
sun as the size of the basketball.
Yeah, that's if you got a grapefruit-sized sun. We've got
We
a
now have the
9-foot-sized sun.
9-foot sun. Because that was the sun size we need
So
to
scale
match
a grapefruit
the size
to
of
9
this.
foot, and this
Go ahead,
distance
what do you
to
think?
350
pretty darn
yards.
close. The actual, one more guess?
What was the guess?
350
yards.
It's,
Quarter mile.
yeah, you guys are closing right in. It's 977 feet.
Shall we switch
So-
the slide?
Now you can switch the slide. So this is if we were centered right in this room with the sun here, a 9-foot sun here. Mercury, Venus, Earth would be this far away. So you're running on the other side of the lacrosse field. And can anyone see? Do you have the pointer?
No.
Barely see it.
Okay. Let me see if I can get the laser pointer to work. Where's the laser pointer? The
Just
button in the
fiddle
front.
with it until it works.
That right
That one. Got it. All right.
It works sometimes.
Well, what you're looking for is that little tiny black dot right there. That's the moon. This is the orbit of the Earth, the green line, and the moon is 30 inches off of that line, and it's a little tiny thing. So we could not put our 9-foot sun 977 feet away and still be talking to you inside this room. But we can still represent what the shadows would look like. So now we need
A
some
sun.
illumination.
I can give you the sun.
Do that. All right. So we're going to just pretend this is the sun for a minute. Okay, Alex, here's your goal. We need to turn the other way. Okay. Now,
I'm going to stay here and help you.
okay, so let's straighten up the Earth. The Earth is falling off. Okay, Alex. The illumination, the light is coming this way. It's going past the moon, and the moon is leaving a shadow. Can you?
The shadow onto.
He's actually doing it.
doing it.
He's doing it really well. All right, now Frank, yeah, go ahead and move out of the way, Frank.
Oh, I'll get out of the way then.
Because what you want to do is let them see what you're doing. Can everybody? It's going to be hard for those of you in a straight line, but
Alex, take it off. Take it
He's
out of
got-
alignment for them.
got the Earth there, and there's the moon. But you can imagine how closely he's holding that, how difficult it is in real life if planets and moons are moving around, the sun is moving, things are turning, how very rare it is to actually get these things to line up properly so you get a total eclipse. Okay, Alex, I'll take this from you. Turn around. That way. Face the audience. Take a bow. Everybody applause. Thank you, Alex. All right. So that was this activity. If you're interested in doing this activity, you can look for it. So, oops, sorry. That's not the pointer. Are you doing that too? Okay,
There we
we won't
go.
both do it.
I got it.
The Night Sky Network has this online. This will also be on the slides, the link for you to go and do this activity. Just takes a yardstick, though, a 1-inch ball, a 1/4-inch ball, and a couple of clips, and a stick. All right, thanks again, Alex.
All right.
That's my part.
All right, so now that you've got a scale of it, let's take a look at some interesting views of eclipses because we're used to these. And yes, these are gorgeous, and I never get tired of looking at them. But recognize that's an earthbound perspective. And we live in the space age, right? So we don't have to be bound by an earthbound perspective. So watch this. Here's a view of a total solar eclipse from space. This is from the Discover satellite, NASA's Discover satellite. And it watched a total solar eclipse. When was this? March 2016. I'm going to go backwards just so you get to see. There's the shadow moving across. Is the spacecraft out at L2? Ah, a million miles. That's L2. Right. Well, actually, it would have to be L1. Take it back. If you're going to see the sunlit side of Earth, it'd have to be L1, not L2. So that's kind of cool. All right. And so that gives you a feeling for what it's like to see the total solar eclipse from space and over time. What's also cool is if you just watch it over time from Earth, and there are quite a number of these types of photographs. These are time lapses where they watch the partial eclipse. They have the total solar eclipse and the partial eclipse. The guys who are really into astrophotography compete to try and come up with the coolest way they can do these type of things. So if you search online, you can find an amazing number of these. One of my favorites is from Fred Espenac, Mr. Eclipse, and he got this. And notice that he had to switch to a different. You're using a solar filter throughout here. All right, and you actually take off the solar filter in order to take the shots during the total solar eclipse of the corona. Just like, well, we'll tell you later, you can take off your solar eclipse glasses only during totality, all right, to get these kind of shots. All right, so how often do these eclipses? I keep telling you that they're rare. Well, here is a list of all, here is an accounting of the solar eclipses during the 20th century from 1901 to 2000. There were 228 solar eclipses around the world. 78 were partial, 73 were annular, 71 were total, and 6 were hybrid. Hybrid means that it appears total in some parts and appears annular in other parts. Okay? And this actually surprised me that it was split third, basically, for partial, annular, and total. I thought that the partials would be more dominant than this. And the longest totality was in June 1955 of 7 minutes and 8 seconds. The theoretical longest possible total solar eclipse is 7 minutes and 30 seconds, around there, maybe 7 minutes 32 seconds. So we got a very long eclipse. Anything over 7 minutes is an amazingly long eclipse. Okay. You get up to that. The largest number of eclipses in a single year was in 1935 when there were 5 solar eclipses. They were all partial or annular. And then there were actually 2 solar eclipses in a single month in July 2000, on July 1st, and then again on July 31st. There were 2 solar eclipses. All right, so this gives you a feel for it. You know, there are a couple of eclipses a year, but they're spread out across the globe. And what's fun is to look at the distribution of them, well, let's say relative to the United States. So this is from 1951 to 2000. Here are the paths of the total and annular solar eclipses, okay? So the blue ones are the total eclipses. This is the path of total eclipses. And the yellow ones are annular eclipses. And you notice where they end is where, you know, you stop being able to see them, okay? So there was a, 1970, there was one that, the total eclipse that swooped off the East Coast. But we had no coast-to-coast eclipses in the 50 years from 1950 to 2000, okay? You go from 2000 to 2050, and we got 2 coast-to-coast eclipses. We have the 2017 one here, all right? We're also going to have one in 2045, and plus we're going to have this one swooping across the United States in 2024. So you kids, you're alive at the right time, okay? Your parents did not get some really good eclipses here in the U.S., okay? But you guys are going to have some seriously cool eclipses in the next few decades here, all right? And this sort of just shows you that if you hang around in a place, it's not too likely to get a total solar eclipse. I'll give you that number later on, all right? And one of the main questions we often get is, why don't you get an eclipse every month? If the moon is orbiting Earth and the moon goes between Earth and the sun every month, how come we don't get an eclipse every single month? Okay? Well, there are a couple reasons for that, and let me go into them. First of all, is phase, okay? It has to be in the new moon phase. We'll talk about these. There is position, All right, it actually has to be on that line, and then it has to be distance. Okay, in order to get similar eclipses, it needs to the moon has to be at the same distance. Let me go into these in a little bit more detail. So, the phases. All right, we know the moon goes from, we're used to full moons, all right, and it goes through gibbous to third quarter to crescent, goes to new moon. That's when it's between Earth and the sun, to crescent and quarter and gibbous again, all right? So we get around this. We can only have eclipses there, so that limits it to once a month, all right? This is called the synodic month. The time between new moon and new moon is the synodic month, and it's 29.53 and ... days, okay? That's our first ingredient. Second ingredient is that the moon's orbital plane, this green plane here, is inclined to the Earth's orbital plane. So the Earth goes around the sun in what's called the ecliptic plane, this blue plane, and the moon goes around Earth in this green plane, and they are tilted, all right? And where they intersect is called the line of nodes, all right? In order for there to be an eclipse, the moon has to be close to this line of nodes, all right? So that when the moon is on the line of nodes here, you get an eclipse. But if the moon is on the line of nodes here, you won't get an eclipse. All right, at new moon you wouldn't get an eclipse because it would be above or below the plane. Okay, you could get an eclipse here and no eclipse here. So the line of nodes orbiting around the sun is another ingredient. However, the line of nodes itself actually precesses a bit. It rotates in the frame around Earth. So if we combine that, the line of nodes going around the sun and the precession around Earth, you actually get what's called the draconic year, from when the line of nodes lines up with the sun to the next time it gets to the same point to line up with the sun, and that's 346 days. Okay, this is not 365. It's not a full year. It's 346 days. It's called a draconic year. That's element number 2. All right. Finally, the moon's orbit is elliptical. All right, it goes from its closest point, perigee, to its furthest point, apogee. All right, and the size of the moon matters. All right, if you have a very small moon when it's out at apogee, you'll get an annular eclipse. If you have a very large moon when it's near perigee, you'll get a total eclipse. Okay, and by the way, how many of you have heard these things about supermoons? Okay, this is a supermoon. This is a mini moon. See the huge difference there isn't between them, okay? All right, when people talk about supermoons, they're exaggerating, okay? This is the true difference between the biggest moon and the smallest moon, okay? Which affects which type of eclipse you're going to get. So, this is called an anomalistic month. It's 27.5 days to go around in its orbit between its position. So, the lunar cycles that are affecting are a synodic month, a draconic year, and a anomalistic month. And let me tell you, yes, I had to learn this terminology myself to be able to give this talk. It's not something most people have at the tip of their tongue. All right? So with computers, of course, we can these days predict exactly when eclipses happen. However, the first people to be able to reliably predict eclipses were the Babylonians. About 2,500 years ago. They had no computers. They had no integral or differential calculus, okay? They did, however, have records dating back 1,000 years of eclipses. This, I'm told, is a tablet that has some eclipse records that go back as early as about 1600 BCE. All right? And from that, they deduced that there was a Saros cycle. Okay? That there were patterns of similar eclipses that were 223 synodic months apart, which corresponds to about 18 years, 11 1/3 days. Okay? They could find in these records these 18-year patterns of eclipses. All right? And this is the first time that eclipses became predictable. And I say that was good for their kings, bad for their substitute kings, and let me tell you why. This is a quote I found. The importance of these predictions cannot be exaggerated. The Assyrians and Babylonians regarded lunar eclipses as evil omens directed against their kings. Now that they were predictable, it was possible to appoint substitute kings who would bear the brunt of the god's wrath. The real king would remain unharmed, and the continuity of the state's policy was guaranteed. The poor man who was appointed as substitute king was killed. In this way, the omen was always right. Anybody want to bet whether Trump appoints a substitute president for the eclipse this summer? All right. So they were able to predict this, but why should there be an 18-year pattern? It's because, well, let me have an example. Okay, so these are patterns of eclipses from 1990 to 2000. All right, and if I just take the top and the bottom, they're 18 years apart. And if I show you, all right, well, the pattern of eclipses here looks like the pattern of eclipses here. And same here, except for this one seems to have slipped a month. All right, and the same over here. You can see that there is this pattern. Why should it be there? Why is there this Saros cycle? Well, 223 synodic months are 6,585.32 days. It turns out that 19 draconic years is the same thing, 0.78, by about 4/10 of a day off. And the anomalistic month, 239 of those, is the exact same thing, but only 2/10 of a day off. This is an amazing numerological fact that these three periods at this period of time multiply together to get almost the exact same time. So this produces what we call the Saros cycle, and this gives you Saros series, these series of similar eclipses that are 18 years apart. Here's an example. So these are 9 eclipses from the Saros cycle 136. All right, and the first one here is in 1901. The next one's 1919. This one will figure importantly in a second. You'll notice it's 18 years apart. It's also a third of a day off, so it's moved a third of the way around Earth, right? Okay, and here's 1937, 1955, and you can see that it moves a third of the way around Earth, but it also moves north. This series is moving, all of the eclipses are moving just a little bit further north. Okay, the Saros series lasts for about 1,600 years and have on order 75 to 80 eclipses in them. Here is an animation of Saros cycle 145. All 77 of them, I believe there are in this. And it starts around in the 1600s and finishes around the year 3000. Okay, and you can see how these Saros series progress, and the similar eclipses just move just a little bit every 18 years, or really, if you're going to try and be in the same area, every 54 years. All right, so that's the science behind it. All right, so what can we do in science with these eclipses? All right, eclipses involve right triangles, okay, trigonometry. All right, and using the angles involved here between the sun, moon, and earth, and you got these right triangles involved here. During a solar eclipse, well, you can definitely tell the relative size of the sun and moon. Okay, this was able to be done in the time of the ancient Greeks. You could also, using a lunar eclipse, as the moon passes through the Earth's shadow, then calculate the relative size of Earth and moon. And we talked about that earlier in terms of understanding the relative sizes. What is really important about the eclipses is that it was, up until a certain time ago, the only way you could see the solar corona. This is an eclipse from 1860. A drawing, you can see the prominences here around it, and you can see the flows in the solar corona, including this nice swirl here, which I think sort of matches this solar outburst seen by the SOHO satellite in 2003. Fortunately, we're in the space age these days, and we no longer need total solar eclipses in order to be able to see the solar corona. We are able to monitor it. This is from the LASCO experiment, the LASCO experiment on the satellite, to be able to monitor both the inner part of the solar corona and the outer part of the solar corona. So we can see that. But by looking at the solar corona in the 1800s, they were able to discover the element helium. This is kind of cool, all right? So this is a rainbow, the spectrum of the sun. Well, it's not actually the spectrum of the sun, because the spectrum of the sun actually has these black lines across it. These are the spectral lines due to elements in the sun's atmosphere, right? And by examining those lines, you can tell what elements are in the solar atmosphere. So, for example, hydrogen has one electron, and as it bounces around inside that atom, it can only emit specific wavelengths. It has specific energies in those orbital changes. It can emit specific wavelengths, and these are the visible light wavelengths that hydrogen can emit. Here are the visible light wavelengths that neon can emit. So we have these signatures of these elements due to their spectral lines. All right? And so when you look at the sun's atmosphere, sun's spectrum, and you see these spectral lines, you can determine the elements in it. Well, this is a simplification. This is an actual solar spectrum from the National Solar Observatory. And it's actually just incredibly football field long spectrum sliced up into pieces and then stacked. And you can see the various elements. Like you see these two lines here, those would be those two lines here in the yellow here, all right? And you can go through this, and what they did in the 1800s, they took spectra not quite as good as this, and were able to identify the elements in the atmosphere of the sun, except they were left over. There were some lines that they couldn't identify with any known element. It was an unknown element they were seeing in the atmosphere of the sun, and the Greek word for sun is helios, so they named that spectrum helium. Helium was discovered in the spectrum of the sun's corona before it was discovered here on Earth. Cool. One last thing that we are able to do with solar eclipses, and that is to confirm general relativity. So Einstein's paper on general relativity came out in 1915. And without going into any of the mathematics, my three-word summary of general relativity is mass warps space. Okay? That's all you really need to know as a member of the public about general relativity. So that means if space is warped, then the light that passes through warped space will actually curve. Light that passes near the massive sun will bend. So if we're looking at a star, all right, we're looking past the sun towards a star, and its actual position is here, that light ray will actually bend a little bit as it passes the sun, and its apparent position will be over here. If its real position may be here, but we'll see it apparently there due to this warping of space. Well, the sun is too bright. We can't see stars next to the limb, except during a total solar eclipse. So Einstein's paper came out in 1915. In 1919, there was a total solar eclipse, one of the ones that I pointed out earlier. And there were expeditions to go and measure the stars around the sun. This is an actual depiction. This is an actual photograph from it. And these white lines here indicate stars that they measured in terms to find their positions during the total solar eclipse. They then went back a few months later and measured those exact same stars. So during the eclipse, the light was bending. A few months later, when the sun wasn't there, the light wasn't bending. There were deviations in the positions, and those deviations matched the predictions of general relativity. This was the first verification of general relativity. 4 years after it, that it was able to predict the bending of light as it passed by the sun during a total solar eclipse. All right, so general relativity passed that eclipse test. It has since passed many other tests along the way. So that is all of our background and history for you. Now let's take a look at what you ought to do in order to plan for where you want to figure out where you want to be for the 2017 solar eclipse. Jess, you want to come up and give this part?
All right. Can y'all hear me all right? Y'all still awake? Barely. Okay, so in preparing for the solar eclipse, the best thing to do is know what things to look at. So this is an animation where you can see the path of totality going across the U.S. So it's going to hit the west coast in Salem. So if you need. We lost your mic. Lost my mic. Better? Just higher up? Okay. So So you can, this is a really cool animation. So you can just kind of see how it's going across the U.S., hitting Oregon, my home state, woo woo, and kind of going across. This next animation is the same thing.
Jess, you wanted to, the finish of that animation had
Sorry.
had the partial lines.
Sorry. How would I play that again? You want to zoom to the end?
Yeah, I can zoom
So
to
then-
the end. We wanted to make sure that they saw, we want to go back.
Sorry. I
That
think
one.
you clicked it. Yeah.
There we go. Yep, I'm going to say there. There you
Oh,
go.
sorry.
We wanted them to see those lines.
So the partial eclipse. So these are the percentages here. So it's the total eclipse here, if you're in these regions, and then 90%, 75%, 50%. So most of the U.S. has more than 50% that you'll be able to see. Okay? Okay, so this is again the same path, but it's showing exactly what you would see in these different regions of the U.S. So again, it's going across the U.S., and then you can see the different regions and how it would look as it goes across. So it's really cool.
And I got one for Baltimore.
Yes, and so we'll wait for it to hit Baltimore. So it's not as good in Baltimore, but how many of you guys are planning to see the eclipse? Most people in the room? Yes. I just want to kind of take a poll. Anyone kind of going, do you guys want to shoot out to me some of the places you guys are going to go? Charleston? Nashville? Nashville's a good one. Kentucky? Casper? Okay. It's a huge range. It's awesome. So you guys kind of know this information already. But just in case you guys want some more resources, some of the handouts that we gave you guys today have the links here. This is just the one from Goddard. It's not on this one. But if you guys want to write this down, or if you come across, if you're just Googling it, again, some more information. It has an interactive map where you can actually see exactly the time of each place, totality in each place, and then the regions throughout it. Okay, so this one.
This is an example of that.
Yeah, so it's an example of this map here. So if you were in Salem, Oregon, it just would show you exactly the location and then the totality and how long, the duration you would see there. Again, Portland's a little out. I was born in Portland, but 99.38 is not total eclipse. It's a partial eclipse, but I think that's still pretty good if you're in Portland and want to see it. And something that Frank keeps saying, that we're at the mercy of the weather throughout this whole thing. So, I mean, if you're in Portland or you're in Salem, you know, it just kind of depends. So here's the one for Baltimore. We don't get really good. We get 79.19% totality, so a partial eclipse there. Again, it starts at 1:18 p.m. and ends at 4. So if you're traveling, again, like I was saying prematurely, that we're at the mercy of the weather. When you're going to the different locations, make sure that you want to be as close to the center line as possible to see the full eclipse. Checking routes, making sure that, like Frank was saying earlier, if you're planning to go on the trip, make sure that you're really enjoying the vacation that you're going on, just in case you don't get to see it. It would be a bummer if you can't. But again, we're at the mercy of the weather. But a lot of, like Frank was saying earlier, a lot of people will be taking pictures of this and videoing this, so there's many opportunities to see it if you plan not to go anywhere. So observing, was this?
I don't know.
I'll turn it back over to
I
Frank.
can't remember whose tag it is, so
Okay.
I'll take it at start. All right. So ideas for where we're going to visit. Now, if you go, or even if you don't go, how might you observe it? Well, the first thing we're going to say, and you're going to hear this from everybody. Oh, microphone. Sorry. Yeah. First thing that we're going to say, and everybody who's doing outreach from the eclipse is going to say, safety first. Looking directly at the sun is unsafe. You can just try it and go, no, I don't want to do it. Okay, yeah. You can use certified solar filters. Okay, sunglasses are not good enough. Okay, sunglasses, no. Certified solar filters, yes, okay? All right, really, really a point to emphasize. There is only one exception to this rule, and that is during the very few minutes of totality, then it's safe to take off those eclipse glasses and look at it. That's only if you're in totality. Okay, if you only have a partial eclipse, the eclipse glasses stay on, okay? If you get into totality, you get those few minutes of being able to take off the eclipse glasses and look and see the solar corona with your naked eye. That's part of the amazing experience, okay? All right, don't look directly at the sun during partial eclipse. We got that? Good. You're gonna hear that from lots of people when you look around the web. Okay. There will be webcams, all right? This is actually from a solar eclipse a few years ago. We have some pointers to where some webcams are, but if you don't want to do anything, if you just want to sit in your basement, you can still view the solar eclipse by using webcams, okay? But I suggest you get out and actually look, because looking is part of the fun. And one of the easiest things to do, anybody can make it so easy, even an astrophysicist could do it, is to make a pinhole camera. Carolyn, this is your I'm tagging you. Go.
Heck, I'm it. All right, and in fact, I have some more props. This is a pinhole camera. You may not be able to tell, but there is a hole there. So this is the simplest way to view something like this. I used one of these a few years ago for a partial eclipse. If you have a small opening here, the larger the distance you have, the bigger the image is going to be, but it'll be a little less sharp. But you will be able to notice the difference in what's happening with the shape of the sun as that bite slowly gets taken out of it. And you can go online to find how to make another type of pinhole camera on a JPL website. There's also ones that there's a ton of different ways to make pinhole cameras. Some of them, you have to wear a box over your head and have the sun behind you. Thank you. I didn't want to show that one. It's a pretty funny picture, not always very effective for little kids because it's not intuitive for them to have the sun behind them if they want to see it, because the box has a hole at the back, the light goes through, there'll be a piece of paper in the front. If you Google pinhole viewers for an eclipse, you'll find many, many, many different versions, but this is the simplest. Okay, one thing just to notice is that with the way optics works, the images will be inverted. But you don't need to have something even like this. If you were just outside, trees provide one of the best pinhole cameras anywhere. All the little spaces between the leaves will provide little crescents along the ground, and they will wave and shimmer with the breeze, and it's really a pretty fascinating picture. You can use kitchen utensils. I'm not sure if you can see it, but each one of these is a little crescent shaped. You can use your hands. Just crossing your fingers together is going to make another small spot. And again, I hope you can see these are little crescent shapes of the light going between her fingers. And that one. And this combines both of those methods, the hands and the leaves. All right, so again, eclipse glasses. There are a lot of different forms of these. You can go online and find a lot of places to buy them. They are pretty inexpensive, but they do need to be true solar lenses. These solar glasses and any of the ones that are certified will block 100% of the UV, 100% of the infrared, and 99.999% of visible light, which means if you're just holding a pair up, you're not going to see anything with regular daylight. And I have a few of those over here, as well as some binoculars. So if you just look at them, they're going to look like there's aluminum foil on the front. They just kind of look gray in the back, and you can't see anything through those, which is a good thing. The sun is very bright. You can also have binoculars. I have a pair of these. And again, just looking through them, you can't see anything. But they also have built-in solar filters. You can use a regular pair of binoculars as long as you have a solar filter on it. And for the telescope portion, I will pass off to Frank.
Okay, that's fine. Telescopes and photography, there are a lot of people who will be doing this. In speaking to the general public, we have to caution that this is generally for experienced observers. Okay, photographing time-sensitive astronomical things is difficult. Photographing astronomy is difficult. Photographing time-sensitive, where you've got to get the timings down exactly, is really difficult. But you can use a telescope with a certified solar filter. You can put the solar filters on your cameras. Notice that the guy who's running the camera has got his Eclipse glasses on top of his other glasses, so he can, look at his camera and then look at the sun and do that all together. But what the folks who really do this in detail tell me is it requires really good equipment, it requires expertise, but it really requires planning, timing, scripting, and rehearsing. Because when you're in and there's just 2 minutes of totality to deal with, they make recordings on, and they play back the recording to tell them what to do when, because you can just get caught up in what you're looking at and not take care of your equipment, okay? It is a totally separate concept in terms of just enjoying it versus working on it. It's very difficult. And if you set up a camera looking at the sun, you never know, you might attract some shady characters. This is a fun one from having a solar star party, and obviously some cosplay folks came by. All right. So in listening to various folks who've done this a lot, here are the pro tips that they would say. Unless you are a veteran eclipse observer, keep it simple. Plan on primarily enjoying the experience of a total solar eclipse. Feel the dusk coming on in the middle of the day. Watch and listen to how nature reacts when the birds start, getting ready to go to bed. Enjoy the magnificence of the solar corona, all right? There will be thousands of internet images and videos much, much better than an eclipse rookie can capture. Now, I know in this audience we happen to have some people who aren't eclipse rookies, who are more veteran, folks from the astronomical societies around here, who know what they're doing, and I wish them absolutely the best of luck in what they're doing. Yes, question?
I don't know how many Esplanade has seen. I've been to 13.
13. So you are qualified to do all this other stuff, okay? Because you know what's going to happen. You can anticipate it, okay? I've seen 2 or 3 eclipses, so I'm not qualified.
Howard Johnson in Richmond.
The back of a Howard Johnson in Richmond. That just sounds like a country western song, doesn't it? All right. However, if you are an expert and you really want to do it up right, you go back to 1973 and you take a Concorde and fly along the umbral shadow, okay? This was just as the Concorde was coming out of beta and going into production. 5 teams of astronomers flew on this Concorde, chased the umbra across it. They turned a 7-minute total eclipse into 74 minutes of totality and were able to observe it. So that's probably, in my opinion, the ultimate eclipse chasing that has ever been done. And since the Concorde's not around anymore, you might not be able to do it again. For that eclipse. Yeah, this was across Africa, right? All right. So now we're going to do a little bit of demo in terms of observing the eclipse. We've got these eclipse glasses and the eclipse binoculars here, and we're going to need another volunteer. So Carolyn?
I actually need 2 volunteers. I need somebody who does not wear
we got
glasses.
one over here.
Okay, you get to be first. I need one other person who does not wear glasses. Grown-ups are allowed? Yes, you may come up too. Fought off all the other volunteers. Excellent. Good. What's your name? David. What's your name?
Sergey.
What is it? Sergey?
Yes.
Sergey and David, say hello. Yay. All right. Okay. Neither one of you wears glasses. Okay. These are already in focus, so don't adjust the focus. Okay, I'm going to let you hold those for now. And if you go searching online for eclipse glasses, you will find from the ordinary to the minion version and all kinds of aliens. Pick one. But sadly, you don't get to keep them. Okay, so what you're going to do, you're going to put those over your eyes. We're going to use the projector again as the sun. So you can tell me if you see anything. No. Okay, go ahead and put the binoculars up. Now what I want both of you to do is leave the binoculars and the glasses on. We're going to turn the projector up and it will get really bright, so I don't want you to look right at the projector. So keep the glasses and binoculars on until I tell you to take them off, okay? Okay. Okay, Sergey? Okay. All right, so let's start cranking the brightness up a little bit.
I see it like,
David, okay, describe what it looks like.
it's like a really small pinhole that's orange.
Okay.
Okay.
Sergey,
can you
see anything yet?
Yeah.
Yes? Very good.
All
Okay,
right.
crank it up a
Let's
little bit
go
more.
with- That's 50% brightness.
Okay, Sergey, what does it look like to you?
It's brighter orange.
Okay. Go ahead,
All right.
turn up a little bit more.
75.
How does it look now?
It looks much brighter.
And there's,
Okay, we'll go
there's white.
last one up. And if I were standing right in line with that, that would be just too bright to see.
All right. And one
So
of the
how
things.
hard is it, Sergey, for you to stay focused or pointed right at the light?
I can see it, but it's very hard to keep still.
It's hard to keep still. That was the one thing I noticed. It's very easy with these glasses to just put them up and you're going to be able to point them perfectly. The binoculars are the 6 power, which is not much, but surprisingly makes things jitter. So just to give you fair warning if you choose to go that way. Okay, both of you can look down at the floor. Okay, now you take them off and you're safe. All right, thank you very much. All right, and applause for our fine volunteers. Thank you.
And we note that that projector is nowhere near as bright as the sun, okay? And it hurts just to, when you put that projector to white, and we were trying it out, and it really hurt us. So that's just an example of how bright, how much these Eclipse glasses will block. All right, final 2 more sections. Jessica gets to do the Eclipse resources.
Okay, tag back in. All right, we know it's getting late, so we'll kind of go through these quickly. For those of you that are going to the Eclipse, many of these you have seen. For those, this is your first time, but just kind of give you a quick rundown. This is NASA's website here, eclipse2017.nasa.gov. This is a lot of resources here, and if you click on this event tab, you can actually go in and see what's happening local. So that's one thing we want to kind of let everyone know, is that if you're not able to go to totality and you're still seeing partial, but you still want to be engaged, there's a lot of activities and a lot of people doing things leading up to the eclipse and, of course, the day of the eclipse. So don't feel left out if you can't go. Like, I won't be going anywhere. So, but again, this website, and if you click on the events tab, you can see what's happening locally. So there's a lot of libraries and museums that are doing events. So if you're interested with your students, or you have schools that you're wanting to participate in, that's a good place to go to. Eclipse, this is the AAS. I was there just last week. They also have a website that they're going to continue to keep updated. All of these websites will continue to be updated with resources and guides. So if you go to eclipse.nasa.gov, .org, sorry, I don't know where I got gov. You can check that out there too. And then this is, what's his name? Fred Espinak's website, if you want to check things out there too. Again, he's been doing this for many years, so if you want to check him out. I know I'm kind of going through this fast, but if you guys want to write them down a little later, feel free afterwards to kind of, and we'll post the slides so you have it.
On the email list, you'll get a link to where the slides are posted.
The NSO, of course, has a website here too. Check out things that they have there, updating, and then I'll turn it back over to Carolyn or Frank. I can do these too. Sure. So again, Carolyn was talking about pinholes, but if you go to the JPL website, you can learn actually how to make a pinhole camera. And this is really interesting when I was learning about the solar eclipse, that they have a citizen science app that you can download to actually study what's going on in nature around you. I thought that was really interesting because animals get kind of really confused. It's getting dark, and all of a sudden it's bright again, like they're wanting to go to sleep, but then they're like, wait, it's sunny again, what's going on? So that's kind of something we may not think about when this is happening. So there is an app that you can download there to kind of capture things. This is really cool. They're doing a Eclipse mega movie that will be, of course, released after the eclipse is done. But if you are very experienced this and you're wanting to take movies, you can add it to this mega movie that they're going to eventually create. It's really exciting. Frank was talking earlier about some webcasts. So NASA has one, all the different ones here. So if you're interested in seeing it live, you're not able to go, it's cloudy in your region, you can check out these live webcams the day of. And these are some places that you can order the Eclipse glasses. There's 3 different websites, but they're ranging from $1 to really high premium glasses up to $50. But if you're interested in kind of buying some resources of your own, here's what you can do. And I'll turn it over to Frank for future planning.
All right, so our last thing is to think about, all right, so we got this eclipse coming here. Maybe it's not convenient for you. When's the next time I'm going to have a chance? Well, for a random place on Earth, a total solar eclipse occurs about once every 400 years. So generally, you're not going to live long enough to hang around and sit in one place and let a total solar eclipse come to you, okay? So you might want to plan and try and do something about it. All right, we have the 2017 solar eclipse that comes across America here. All right, we're also going to have 7 years later, 2024. There's an eclipse where the greatest eclipse is in Mexico, all right, but it sweeps across Texas and through the Midwest and goes off through Nova Scotia. So if you want to take your plane up to Nova Scotia to see a total eclipse of the sun, Carly Simon would approve. You could do it at this point. And this one is a 4-minute and 28-second maximum duration. So whereas this one's only 2017's only 2 minutes and 40 seconds. This one's 4 minutes and 28 seconds. And I said you have to wait 400 years, except if you are in Carbondale, Illinois. You can see here's Carbondale. This is the path of totality for 2017. And this is the path of totality for 2024. They cross right here in this national forest just south of Carbondale, Illinois. So Carbondale, Illinois is the eclipse capital of the world for the next 7 years, okay? All right, they got really lucky. They don't have to go anywhere. All right, as I said, every 400 years, that's statistical, that's not in practice. All right, but there is an even cooler eclipse coming in 2045, okay? And we were talking about this beforehand. Can we hang on this long? This one goes from the West Coast all the way to the East Coast, goes out through Florida. The greatest eclipse is in Florida. The center line goes straight across Florida. All right, it covers from Daytona Beach down to Tampa St. Pete. You could call this the Disney eclipse because you can be in the Magic Kingdom and see a total solar eclipse. You could be in Palm Beach and see the total solar eclipse. It lasts for 6 minutes and 5 seconds, and its greatest time is right here in Point St. Lucie here in Florida. All right? You can even spend this eclipse in the Bahamas, man. All right? This is amazing. And I'm just going, all right, what kind of vitamins and what kind of exercise and diet do I have to do to make it to 2045? A 6-minute eclipse while vacationing in Florida. So that's something to look forward to. All right. I have one final pretty picture for you. We have gone through a whole bunch of things about what you can do to see the eclipse. The important point is to get out and do some observing, okay? To experience it. Sitting back and watching a webcam is possible, but you really feel a greater connection to the cosmos when you get out and actively do it, even if it's just creating a pinhole camera and seeing that partial eclipse like I did when I was 7 years old in Boston. Okay? It's one of the cool things. And really cool is if you are skilled enough to take a picture like this. All right. Thank you for listening. Okay, we have a few minutes left that we can take questions. Peter, what's your question? How fast does a shadow move across the United States? I had that number in my head at one point, and it has since left my head. But we could figure it out from those Goddard Space Flight Center videos, when it hits Salem and when it leaves Charleston, and do the calculation. It's not supersonic, but it's you know, it's got to be moving at hundreds of miles an hour, I would expect. I don't have that number. Anybody else have that number in their head? I'll have it for you next month, and that one I will. That one. Other questions? Yes.
What roughly is the duration function when you're off the center line?
Okay, so going from the center line to the red line, which is the center, to the blue lines. Okay, when you get to the blue lines, you're down to about 10 seconds, 20 seconds. Okay, of course, then it goes to 0 because you get out of it. You do. Notice when we said if you're going to travel to totality, it's get close enough to the center line. Doing exactly on the center line, well, that's going to depend upon the topology of the terrain and the elevation of all that. So just getting close enough. You know, you don't have to be exactly on the center line, but getting close to the approximate center line. It falls off. You can use the Goddard the interactive map to sort of to see how far away it is. The maximum in Salem, just south of Salem, is about 2 minutes. Salem's a few miles north, and it's 1:55. So you know, you'll lose a few seconds for every mile that you're off of it. But you know, just getting close enough to the thing. You don't want to be on the blue line. You want to be closer to the red line if you really can. Okay. However, if you noticed in Salem, you've got everybody from Portland coming down I-5, so I'd stay away from I-5 if I were in Salem. I looked at that map and goes, wow, I-5 is going to be a mess. Question from the way back. Where am I going? The total solar eclipse will go straight through Grand Teton National Park in Wyoming. I already have my vacation booked for Yellowstone National Park for a week before this. I'm following my own rules. If I'm going to take a vacation, I'm going to have a really great vacation. I've always wanted to see Yellowstone. And if we see a total solar eclipse at the end of the vacation, great. If we don't, if we're clouded out, okay, I still had a great vacation. Grand Teton National Park, I will tell you, is booked solid by a group doing the eclipse. I tried to get a cabin at Grand Teton. I was there the first minute the cabins were available, and it was already booked the whole weekend. So there was a block booking before it became available to the public. So you can't go to Grand Teton, or at least you can't stay in Grand Teton. You can go there, but there are no rooms in Grand Teton National Park available. So I will have to be trying to drive down into the morass of Grand Teton National Park on Eclipse Day. We'll see. Yeah.
Two quick questions. Is there any advantage to the $50 glasses versus
Oh,
$1?
yes. If you just buy the paper glasses that she showed you, they're usually in bulk $1, $2, $3, $4. Okay, plastic glasses around $20. The premium, super premium ones that were $50 are just style. You know, camouflage, colored. Maybe metal things. When I said premium, I meant premium in terms of style, not premium in terms of effectiveness. The $2 glasses are just as effective as the $20 glasses, which are just as effective as the $50 glasses. So the paper ones there's no reason to go any further unless you need the style. Okay.
And then, maybe I missed something, but you said some eclipses, the totality of the eclipse would be like 2 minutes, 3 minutes, and others were as much as 7 minutes.
Correct.
What makes that difference?
Okay. It's how close the eclipse is to the subsolar point. Okay. How exact? Well, two major things. How exact the moon is going across, whether it's slightly high or slightly low going across the sun, and two, when the moon is closer, the moon is bigger, so you get a longer totality. Okay. So a perigee eclipse, when the moon is as close as possible to Earth, is going to be the longer eclipses, and then it's got to have the exact right path across it. It can't be slightly diagonal. All right.
The eclipse hits at 9:05 7 hours minus 3.
Okay.
4 hours for 3 seconds.
So okay. So you said 750 miles an hour. All right. So Peter, you got your answer. He says 750 miles per hour. I'll buy that. All right. All the way in the back. Orbiting satellites that will be in the path of totality, I don't know. Go look on the NASA website. I bet you somebody there has probably figured it out. Yeah.
I would urge, if you're near a tree, don't forget to look down. The tree effect is beautiful.
Yeah, the looking through leaves. I didn't even know about that when I was 7 or whatever age I was in Boston, and looked at, and we were doing the pinhole projection, right, and seeing that, and then we happened to notice the trees. Nobody told us about that, and that was a revelation. That is great.
Also, if you can get to some sort of elevation and see what's going on around you from some elevation, it's fascinating too. You really can get a sense of the shadow moving across the.
Even a partial solar eclipse. I was in Central Park for a partial solar eclipse on Christmas Day a few years ago, and even just the partial, it was a 70% or so. You could really feel the dusk starting to settle, the changes in the atmosphere. It just felt interesting.
I'd like to point out that it does not get dark.
No, it does not get dark. Yes, it's just dusk. All right, it's a twilight. It's just a minimum of twilight, actually, on that.
You know, there's one advantage to looking directly at the sun during the partial phase is that you'll get to see it for the rest of your life.
Nobody listen to Peter, okay? Do not listen to Peter, okay? That was a joke. Everybody on the webcast, that was a joke. Okay. All right. If there are no more questions, thank you very much. Join us in February for Priya Natarajan's talk on mapping the heavens. Thank you very much. Yes, love it. If you are new, you may not know that we have lithographs, pretty pictures from Hubble available on table over there and the table down here. Tonight's lithograph is the Interacting Galaxy NGC 7714. If you want to know about, one of your favorites, right? And if you want to know more about the galaxy, there's a few hundred words of text to describe it and another image on the back. If you didn't get one on the way in, grab one on the way out. Also, over there we have some Eclipse information that will tell you remind you some of the stuff that we're going to tell you in the talk tonight. These printouts are over there. You can grab them on your way out. Because tonight's talk is the 2017 total solar eclipse, Chasing Shadows Across America, by myself, Carolyn Slavinsky, and Jessica Kenny. We have a round-robin tag team presentation for you tonight because there is just so much to cover about the solar eclipse. Next month, we have a very special speaker coming in from Yale University, Priyamvada Natarajan, on mapping the heavens. And this is very special. We usually don't have any budget to bring in people from out of town, so when they're willing to come in from out of town and give a talk, this is fantastic. In March, Lauren Corlies is coming not from out of town, but from across the street at Johns Hopkins University, and she has yet to give me the title of her topic. She said she was going between a couple, and she hasn't given me the final title. And in April, we have David Law from the Space Telescope Science Institute talking about integrated field unit spectroscopy. I know that sounds a little intimidating, but as we take advantage of computers and new electronics, we can do amazing things in astronomy, and IFUs are part of the future, okay? So you want to know the future of astronomy? This is a big part of it. To find out all this stuff, you can go to our website. If you just search Hubble Public Talks and Ring Effect. You can also get, at the same time, something called Bailey's Beads. All right? And this is due to the uneven topography on the surface of the moon. There are mountains on the moon. The moon is not this perfect sphere as it was imagined back in ancient Greek days. It actually has topography, and you can see the light shining through the hills and valleys on the moon just as it goes into and out of totality. Here is a nice little time sequence showing from left to right as the moon passes over the various topography of the moon, creating these Bailey's beads. Sometimes also you can actually see the very inner atmosphere of the sun, and this are the solar prominences, because the corona extends well out from the sun, but right above the sun you can get these fingers of hot plasma up from the sun, and these red regions right here, that is that hot plasma seen in H-alpha radiation here, I believe, that's extending above the sun. You can actually see the fingers of plasma extending above the sun when the moon blocks it. This is also, this happens particularly when you have an eclipse that's just slightly an annular eclipse, and I'll tell you what an annular eclipse is on the next slide. All right, an annular eclipse is sometimes when the moon is a little bit further away and can't cover the entire sun totally. All right, it doesn't become a total solar eclipse, so you get this thin ring around it, okay? And so when the moon is just at the right distance that it just gives a tiny little bit of annular around it, that's one of the times that you can see these prominences extremely well, because you just get a little bit of the photosphere and the material extending above it for these solar prominences. So a total solar eclipse is an amazing event. It is a very rare astronomical occurrence, and folks who've been to them can get really religious about them, okay? And Friday, that I just wasn't able to make the time to do News from the Universe, so I apologize. I'll give you a really great one next month, okay? All right. In the meantime, I will introduce our featured speakers, and I will switch slides. All right, our speakers tonight are myself, an astronomer in the Office of Public Outreach. Carolyn Slavinsky, stand up and say hi. She's an education specialist in the Office of Public Outreach. And Jessica Kenny, another education specialist in the Office of Public Outreach. Is that your title? Education Outreach Specialist. Okay. So we are three of the, 20, 25 people in the Office of Public Outreach. And we recognized when we had this gap in the schedule, we didn't have a talk for January, that we needed to, well, wait a minute, we got this amazing event coming up in August of next year, and we needed to fill that in. So we actually utilized about 6 more people's knowledge in pulling together lots of information about this. Somebody was commenting beforehand, well, this is 8 months away. Do we really need to talk about it now? Yes, you do, because if you're going to go see this total solar eclipse, you want to plan in advance. Matter of fact, just last week at the American Astronomical Society meeting in Texas, where Jessica was there, they had a huge session that was packed, sold out, standing room only session of people sharing information about what they're going to do for this total solar eclipse. So it's not too early to plan. I've already got my reservations for where I'm going to be for this eclipse, and hopefully we'll give you enough information tonight so you can decide where you want to be for this eclipse. All right, so let's start with the basics. There will be a total solar eclipse on August 21st, 2017. It will pass across the entire continental United States. It will start in Oregon and go through South Carolina. It will have its greatest duration in Illinois, Kentucky area, 2 minutes and 40 seconds of total eclipse. All right? This path of totality that is being drawn here is only 71 miles wide. All right? However, the rest of North America, all the rest of things that aren't on this line, will get a partial solar eclipse, okay? This is the first coast-to-coast solar eclipse since 1918. So I'm told. First coast-to-coast total solar eclipse since 1918. All right, there haven't been really good solar eclipses lately in the United States. This is something special. All right, and so what's going to happen? All right, well, this is the first part of it is going to be a partial solar eclipse. This is the limb of the moon passing in front of the sun. And partial solar eclipses are much more geographically common because they can be seen across a much larger region. What makes this eclipse special is that this eclipse will go through into not only cover part of the sun, but cover the entire sun. The moon will cover the entire sun, exposing the outer parts of the sun, the atmosphere of the sun, called the solar corona. And the solar corona is just amazing to behold. If you have really good photographic skills, you can see all sorts of amazing striations. This is material flowing away from the sun in the solar corona. And there's amazing photographs of the sun during a total solar eclipse. This isn't just a black spot put there. That's actually the moon. All right? And you are seeing the material flowing away from the sun in the solar corona. You also could see some other really cool effects. One of the most famous is the diamond ring effect. Just before totality, or just as totality ends, you can get a bright spot with this ring around here. All right, and you get a beautiful diamond. Space Telescope Public Talks. You'll find this webpage where we have the list of the upcoming lectures, the link to the live webcasting, the archive of our webcasting, which goes all the way back to 2005. All right, that's 11 years worth of astronomical goodness for you to explore. And you can also subscribe to our public lecture series announcements to be reminded of things like, oh, hey, we're not having it on the first Tuesday in January. We're skipping to the second Tuesday because nobody was around last week, both because of the holidays and because the American Astronomical Society meeting. So the first week in January is often one that I will postpone 1 week. Okay, email announcements. I already gave you the easiest way to sign up. You can also go to this place, maillist.stsci.edu, to do so. If you would like to send us email, you can send it to publiclecture@stsci.edu, and it will get forwarded along to me and one or two others who answer questions on that email address. All right. Social media, we have on Facebook and Twitter and Google Plus and Pinterest. Do we have others? We may have other social media feeds. I've got my blog on Hubble site. I'm also a little bit on Facebook, Google Plus, and Twitter when I have the time. Certainly did not have any time today, so but I'll get to posting a little bit on social media tomorrow. The weather is not permitting tonight. If you looked up as you came in, you saw no stars. It's clouded out, so we will not be going across to the Maryland Space Grant Observatory after the talk. The Maryland Space Grant Observatory does have a website, md.spacegrant.org, and they do public observing most every Friday. Please go to their website and find their public observing. If you can't, since we can't do it tonight, you may be able to do it on another day this month. All right, News from the Universe will return next month. I know I wasn't here last month to give you News from the Universe, so it's been since November, but we spent so much time prepping this talk today and yesterday and the day before